All right. The next problem we're going to talk about is elastic collision. So in an elastic collision, it's a little bit different from inelastic. What's going to happen is you're going to have two objects, they're going to collide. And instead of sticking together, they're going to bounce apart. So here we have something called an elastic collision. So initially, let's say they have different masses. One has, let's say, positive 10 meters per second. The other one has negative 10 meters per second. And they're going to bounce and hit each other. But we have absolutely no idea at the moment what their velocities are. But we want to find out. So what we could use is the stuff that we knew before, which is momentum initial is equal to momentum final. But we also have a new property, which is mechanical energy. So in this case, mechanical energy is equal to final mechanical energy. And this is true for elastic collisions because when they bounce, both objects are going to retain their shape. They're going to have the same amount of energy because nothing got transferred. And in inelastic collision, when they stick together, some energy was required to make them stick together. So I guess a perfect example is a car crash. So when two cars collide with each other, they don't just bounce, they actually just kind of crumple together. So a lot of the mechanical energy was changed into internal energy for deforming the cars, making them stick. So in an elastic collision, none of that deformity happens. So all the energy is conserved as mechanical. So we could say momentum is conserved and also say mechanical energy is conserved. And that's actually very helpful for us because when we set it up, you'll notice it's a little bit different than the inelastic collision because they bounce apart. We actually have two unknowns, VA, which is also unknown, and VB. So we don't know these things. So we're going to figure out. So let's set it up and you'll kind of see it. So initial momentum is MAVAI plus MBVBI. Momentum final is mass A, velocity A final, plus mass B, velocity B final. It looks intimidating, but once you plug in numbers, it actually reduces in the amount of unknowns. So we do know mass of A, which is 3 kilograms, times the velocity of A, which is positive 10. Do the same thing with ball B, 2 times the velocity of negative 10. And we could plug in the masses here even though we don't know the velocity. We know that mass of A is 3 VAF plus 2 VBF. Simplify it. So you have 30 minus 20 equals 3 VAF plus 2 VBF. You have 10 is equal to 3 VAF plus 2 VBF. So here we can see that we can't solve the problem with just momentum. We have two unknowns, one equation. So we're going to recruit the other property of elastic collision, which is mechanical energy is conserved. So I'm going to do the same setup. Remember, for mechanical, in this case, nothing's stored up on a hill. Gravity's not working to move anything up or down. There's no work in the vertical direction. Everything's horizontal and it's in motion. So we're just going to use kinetic. So kinetic energy of the ball here, which is 1/2 MAVAI squared, plus the kinetic energy of the second ball. And it's going to equal the kinetic energy at the end. So 1/2 mass of A, velocity of AF squared, plus 1/2 mass of B, velocity of BF final squared. And it looks really dirty, but we can make things a little bit simpler from the get-go. All of them have 1/2, so if you multiply both sides by 2, you get rid of that fraction. Makes life a little bit easier. So if you don't have to find the exact energy for each individual ball, you could kind of just ignore the 1/2. Then let's plug in everything that we know. So mass of A is 3, velocity of A is 10, and you want to square it. Mass of B is 2, velocity is negative 10, and you also want to square that, and then plug in these masses over here. So 3 times VAF squared plus 2 VBF squared. Simplify this side, you have 300 plus 200 equals 3 VAF squared plus 2VBF squared. This becomes 500. Now, we have the same situation as the other side, or the momentum side. We have two unknowns and one equation. But we have two of these equations, so technically we have two unknowns and two equations. So we can solve for one. So momentum's easier to solve because there's no square. If you solve for energy and plug it into momentum, you have to deal with the square root. But when you solve for here, you don't have to. So 10, and we'll move one of them over. Pick one, it doesn't really matter. 3VAF equals 2VBF. Move the 2 over, so 10 VAF over 2 is equal to VBF. So we isolated one of the variables, and we're going to plug it in over here. So we have 500. I'm going to do blue so you can see what's going on. 500 is equal to 3 VAF squared plus 2, and we're going to enter what we solved from momentum side, which is 10 3VAF divided by 2 squared. All right, so we just have to square that and then see where it leads us. 500 is equal to 3VAF squared plus 2 times this whole thing squared. So 10 times 10 is 100. 10 times negative 3 is negative 30, but we do it twice, so negative 60 VAF. And then negative 3 will multiply itself, so you get positive 9 VAF squared. Square the bottom, 4. Multiply, and then we could reduce this one to 2. Multiply everything by 2, so 2 times 500 is 1,000. 2 times 3 is 6. Then we just write this one out. 100 minus 60 VAF plus 9 VAF squared. Combine like variables or terms. So VAF squared, you have 9 and 6, so that's 15 VAF squared. There's only one VAF, so 60 VAF. I'm going to move the 1,000 over to the other side, so you get 900, all equal to 0. Get rid of 15. So 15 is, you have 0 equals VAF squared. I believe that's 5. And that one is 60. Then you want to factor it. So what times what gives us 60 with a product of 5? Let's see. Oops, I messed up here. This isn't 5. This is 4. Almost messed up. I was about to say I don't know any. At 4, much easier. So it'll be 6 and 10. And since the 4 is a negative, it'll be negative 10, positive 6. So you're left with 2 answers. So VAF, in order to make this true, this has to equal 0. So it'll be negative 6 or positive 10. Now, when you do these problems, you'll have 2 answers. And one of them will always give you the initial. So my initial VAF was positive 10. So that means my final is going to be negative 6. Once you find that, you can plug it back into this equation. So 10 minus 3 times negative 6 over 2. And that will be, let's see, 10 plus 18 over 2. And then that will give me 14 for VBF. So we have positive 14 meters per second, negative meters per second for VAF. So I think the hardest part about this is not to make a math mistake. So you just take your time and then go through it and try to solve for it. All right, hopefully that helps.